Okay, so this is from what I call phase one. This is basically the first exam. And this is when we were starting to get used to geometry. So I want to talk about a couple of key ideas here. A lot of these things we've been doing for so long, it's become natural. Like we've done the cross product so many times, we can do a cross product, but it's good to just remind ourselves what you can do with the cross product. Now, please feel free to ask questions, and especially the further back we go, the more questions you might have. But, okay, so what do we need to highlight? Well, make sure you understand a few things. If I were picking sort of two big themes that I would say it's very important to focus on, that you might need a little bit of jogging your memory, it's that in the first part of the course, make sure you understand how to work with lines and planes, and make sure you understand how to work with curves in space. Because those are the things that we often test on, and this really sort of tests your geometrical understanding, particularly lines and planes. So maybe let's focus a bit on that. So when you're after a line, think about what you need. A line is described by two things, a point and a direction. The point is almost always a freebie. So your main effort when you find lines is focus on direction. Now there's two ways to represent lines that are commonly used. There's other ways that are less common, but make sure you understand both. There's parametric form, which says what's happening in each of your directions, x, y, and z. But there's also your vector form. Now in parametric form, you take your points and you slot them into your places here. So x0, y0, z0 is your point. Then you have your direction as a vector. Your a, b, c, those are your coefficients that go in. So point, direction. And it's good to be able to take something from a line and say, I understand how to grab the direction of the line and go back and forth. Vector form is even easier. Point plus t times direction. For planes, you need a point and you need a direction. That direction has a name. We call it the normal. Now, the thing about normal is it means perpendicular. So when you're thinking about the planes, make sure you say, I need to find perpendicular things. How do you make perpendicular things? The cross product. Cross product is constructing orthogonal, and orthogonal means perpendicular. So orthogonal means your right angle. So yes, if we need to make perpendicular things, so if you have to make a normal vector, then what you can do is say, instead of trying to find the normal vector, I'll find two things which are perpendicular to it. Once I found two things perpendicular to it, I say, I'm going to win, take the cross product, I have the normal. Now, of course, when you say I have the normal, it's really I have a normal, because you can scale. Once you have the normal, you get the coefficients. So planes look like ax plus by plus cz equals some number. These coefficients, a, b, c, are your normal vector. So if I have a plane, I can grab the normal. If I have the normal, I can write down the coefficients. How do you get the constant? Plug in the point. So you plug in your x0, y0, z0 in to the left-hand side, whatever comes out, that's your constant. So once you remember, it's like, if I need to find a plane, the game is find two things perpendicular to the normal, and you'll win. That's pretty much what this is saying. Okay, so for curves we describe, parametric curves, we have a particle moving through space, and we describe its position at any given time. So we have a couple of things. The function, r of t, it's a vector value function that tells us position. R prime of t tells us velocity. R double prime of t tells us acceleration. And then we can do various things. So for instance, we can find a tangent line. So we think back, if we're looking for a line, what do you need? Point and direction. Where do you get the point? You plug the time into your position function. Where do you get the direction? From the velocity function. So the velocity is the direction of motion. So if you're saying, oh, I want to find a tangent line, I know how to find point. I know how to find direction. Comes from the function and the derivative. If I want to find distance, so distance along a curve, or if you like, that's arc length. You can say, oh, to find arc length, integrate speed. Because you can think of it, arc length is like distance. If I want to find the total distance, I integrate how fast I moved. So the integral of speed. Well, r prime of t is velocity. Magnitude of r prime of t is speed. So as a reminder, all vectors have two key features: direction and magnitude. And so it's important for you to think about, what does each thing represent? What does the direction indicate? What does the magnitude indicate? So in velocity, direction indicates where you're moving, in which way you're moving. Magnitude indicates how quickly you're moving in that direction. You can also do these last two little equations here. This a sub t equals the derivative of magnitude r prime t. This is your decomposition of acceleration. Yeah, I suppose you should know that, but they put it on finals before. It's not the funnest question, but we tend to avoid that. That's my own opinion. Know your basic shapes. Know what these cylinders look like. Know what spheres look like. Know what cones look like. You don't have to remember all the quadric surfaces. I think that's been a topic that was removed. But you still should remember what a cone looks like. You should still remember what a sphere looks like. You don't have to remember any formulas for like the volume of a cone or volume of a sphere. Do you remember the volume of a sphere? Oh, well, I guess we could have left that off. How about the volume of a cone? Okay, good thing we left that on. Okay, yeah. 1/3 pi r squared h. Yeah. Yeah. Oh yeah, it's a cylinder times a third. Good. A couple of other things looking at what's on the list. Make sure you understand the dot product. It can be very useful for testing orthogonality. How do you know if two things are orthogonal? Dot product is 0. If you take a dot product of a vector which itself, you get the length of the vector squared. You can also do projection. And in particular, if you ever have a problem asking something about angles, dot product is useful for that. For a cross product, we've already mentioned the orthogonality, that's direction. You can use it to find area. It's the area of a parallelogram. And if you want a triangle, spoiler alert, a triangle is half a parallelogram. So that's useful. Let's see, what haven't we talked about? We haven't really talked about coordinate systems. Polar, I think, is something that we just assume you know coming in, but it's useful to remember. Cylindrical is polar plus z. And spherical, that's the one that often throws a lot of people off. Theta does the same thing as polar does. It tells you how much you're sort of spinning. If you were thinking about the z-axis as sort of, a tack, and you spin around it, that's your theta. Phi is how far you come off the positive z-axis. And rho is how far you go out from the origin. And it's possible that you might encounter one of these three coordinate systems, either polar, cylindrical, or spherical. They often embed those in either the Stokes theorem. Stokes theorem oftentimes will boil down to a polar. The divergence theorem will oftentimes boils down to something either in cylindrical or spherical. Oftentimes, not always, as I think I make a note somewhere later on. But we'll get to that because that's a later on note. Any questions from the first part of the course?
Can you go over an example where you're trying to find the distance between two parallel planes?
Okay. So Can you find the distance between a point and a plane? Okay, maybe we should talk about that. So you can do things. There are formulas here for distance to line and distance to plane. I wrote those down as though I would expect everybody to have this memorized. I don't. Well, I mean, I do now because I've been teaching this for like 15 years. But I don't recommend teaching it for 15 years before you take the final. You know, you'll have to take it before then. So you can just think of geometry. So let's see, we can probably draw a little bit over here. We have space, right? Okay, so if you're thinking of point to a plane, and there is this handy-dandy formula, but if you forget it, you can just think about, okay, what can I do? Well, if I have a point and I have a plane, what are some pieces of information I have available for me? The normal vector. Okay, so that's something I have in my hand. So I say, okay, I have the normal vector. Can I use that to my advantage? How can I use that? So a vector is a direction. What's something I can do with the direction? I mean, I can make a plane, but I can also make a line. So I can use the normal vector with the point to make something which goes through the point I was given, and it has to hit the plane in a perpendicular fashion. So essentially, whenever we're talking about distance, there's always a right angle built in. And where these formulas come from is it comes from right angle and using either the sine or the cosine. But if you don't remember, you can always just say, look, I'll just figure it out this way. I can make my line. Once I have my line, what can I do? If I have a line and a plane, what can I do with those two things? I can find where they intersect. They might say, well, how can you find where they intersect? Well, take the formulas. So here's x. Take whatever x is and plug it in for x. Take whatever y is and plug it in for y. Take whatever z is and plug it in for z. Now I can find the point on the plane which is closest. So it's really, I can get to this distance here. So that's one way to do it. If you don't want to remember the formula, I can derive the formula. It only takes a few minutes if you want to see where this formula comes from. But now you said, what if I have two planes? That was your original question. Well, there's this classical approach in mathematics called reduce to a previously solved problem. If I have two planes, how can I reduce it to a previously solved problem? Yeah, just pick a point on one of the planes and say, what's the distance from that point down to the other plane? And then you have the distance between the two planes. You might say, but wait, how do I know which is the right one to pick? And the answer is, all of them are the right ones to pick, because they're all equally far away from the other plane. It's sort of like two, pair of parallel lines. As we have the equal sign. Do you ever wonder why we use the equal sign? It's two parallel lines, and if you go to like old books, they really made it obnoxiously clear. They made their equal signs really, really long, because they said, what could be more equal than two parallel lines? But the punchline is, it's the same distance no matter where you are between those two parallel objects.
Wouldn't, for two parallel planes, the distance between them just be the change in d in that equation?
Almost.
Gotta add the...
So the challenge is, it's not just the change in d, and I'm going to try to convince you that it's not. And then I'm going to point out roughly what it boils down to. So it's almost a change in d. The problem is this unique, this answer for the plane? Is there more than one way to write the formula and still be the same plane? What can you do? You can scale. You can multiply everything through by a number. So if I have two planes, I can multiply the second equation by any number I want, and it's still the same two planes, but now the constants have changed on the other side. So the difference between them has changed on the other side. So that's why you run into trouble. Now what you do is you have to scale to the right point. So if you scale them, then you're okay. Now you might say, how do I scale? Well, you essentially have to make sure that this A, B, C on the left-hand side comes from a unit vector. So you have to scale both sides to do that, which is about as annoying as this process. So, other questions? All right. Well, that was phase 1. So, phase 2, which was kind of the short part of the course. So this was when we got into functions, and we started talking about applications of differentiation. So we have surfaces now, and not just things which are flat planes or spheres, but we had z as functions of x and y. So make sure you know how to work with functions. How do you identify the domain? Well, instead of thinking about where it works, think about where it fails. What are the 3 things you have to avoid? Negatives inside of square roots. Division by 0. Yeah, and natural log of anything less than or equal to 0. So if you say, I have a domain problem, start thinking about your problems, things you want to avoid. And if you figure that out, then you're good to go. If you need to do level curves, this oftentimes is a good matching type question, because it was a matching type question on the second exam. It just says, set the function equal to a constant. What does the curve look like? Then we started getting to the derivative, and we said, okay, hey, you know all those things you learned in Calc 1? We're just going to do them again. And the only thing is we have extra stuff floating around. But when we take derivatives, we always take it one variable at a time. Treat the other variables as if they were constants. Okay, great. How do we do things like implicit differentiation? So in other words, suppose you had some expression, we'll just make something up, z cubed plus sine of xy equals 2z plus 5, I don't know. It's whatever. How do you find something like partial z partial x? Well, you say, look, I have a thought. Even though I can't solve for z here, well, you almost could, but you don't want to. Even though I can't, I can think of it as though I could. And then once you have that thought, then it just says, hey, if I want to find partial z partial y, you're going to take the derivative with respect to y on both sides. And just anytime you take the derivative of z, you're thinking of z as being a function of x and y. Carry that through, and that's how you handle implicit differentiation. It's the same thing you did in Calc 1. Now, what's a little bit spicier than Calc 1 is the chain rule, because that is more involved. Because the chain rule in Calc 1, if you were thinking of this in terms of like a tree, in Calc 1 you'd say, oh, I have my function f, which depends on x, which depends on u. And so then I would say, if I want to find the derivative with respect to u, I just say go down the tree, partial f, partial x, partial u. But now we could have a function saying depending on multiple variables. Maybe it depends on x, y, and z. And maybe each of those depends on variables, u and v. So you have a decision tree. Well, not quite a decision tree, but this variable tree. And now you can use that to say, how do derivatives relate? So you start saying, well, if I want to find the derivative of the function with respect to, I marked here v, say, all right, I just find where all the v's are down at the bottom of the tree, and I follow down from the top to the bottom. And every path becomes a term. And every edge on my path becomes a derivative. So partial f partial x, partial v. Partial f partial y partial v. Partial f partial z partial v. And once you understand that, say, okay, now I have my basic formula, and then you fill in as you need. And then you're good to go. So if you see a chain rule problem, draw a tree. And they have had chain rule problems in the past. In fact, most things have had problems in the past. So don't be like, oh, they'd never ask that. They might. They might. Gradient. So gradient is acting like our derivative. And oftentimes we don't usually ask a gradient question because we use an application of it. So a gradient, it's a vector. And now we say, okay, well, great. Vectors have two things. They have direction and magnitude. What's the direction of the gradient telling you? Well, it points. And it says, that's the direction you should go if you want to go up. So the gradient, it's very optimistic. It's pointing to the direction of greatest increase. What if you want to go down? Where do you go? Opposite direction. How do you get to the opposite direction? Negative sign. Yeah, it's an orientation type thing. All right. Now, the magnitude has an interpretation. So the direction is the direction of greatest increase. The magnitude is the rate of greatest increase. So if you ever see something about find greatest increase or greatest decrease, it's a gradient question. But another place it frequently shows up, and this one is just very tempting, very, very tempting problem, is directional derivatives. So, when you see directional derivatives, what do you do? Well, it really says you have two pieces. The gradient and your unit vector. So, what's a unit vector? Vector with magnitude 1. What's the clue that it's 1? Unit, right? U-N-I. You know, it's like unicycle, one wheel. Unibrow, one eyebrow. Unicorn, one corn, right? That's the way you remember these things. So unit, 1. Okay, so if you have a directional derivative, you say, find the gradient. Find your unit vector, and you might have to scale it to make it a unit vector. How do you scale a vector to make it a unit vector? Divide by its magnitude. Take the dot product, and life is good. All right. Tangent planes. Now, tangent plane has another name. Linear approximation. Sadly, they took off a topic. They didn't take off linear approximation, I don't think, did they? But they did take off Taylor polynomials. I know. I feel the same way. I, too, am sad about this news. But what Taylor polynomials are, tangent planes are actually Taylor polynomials. That doesn't mean tangent planes are off limits. I'm just saying tangent planes are a special case of Taylor polynomials. And there's two ways to go about finding tangent planes. You have your general two cases. You have z is a function of x, y, and you say, I want the tangent plane at a point. Well, then it's a matter of the value of the function plus the rate of change in the x direction times x minus a, rate of change in the y direction times y minus b. You can think of this as rate of change times amount of change, because that's what you're doing. More often, and a little bit easier, is if you have a function f of x, y, z equal to a constant. So this is usually like implicitly defined surfaces. In that case, you say, well, how do you find your tangent plane? Well, you got to find the normal. What's normal? The gradient. So the nice property of gradients is you say, oh yeah, it points in the direction of greatest increase, points in the direction of greatest increase, perpendicular to the gradient, there's no increase and no decrease. You're 0. So that's why it's perpendicular. So if you're looking for a tangent plane, almost always go to the gradient. That's your go-to point. We have critical points. that's where interesting things happen. So critical points, we tend to fall into the gradient is 0, gradient is undefined, or boundary. But when we talk about find and classify critical points, we really are focusing just on the first case. So most often, when we think critical points, think gradient equals 0. So how do you find? Well, you're saying the gradient equal to 0. So you solve. And you have the gradient being 0 means that every term in the gradient is 0. So that means all your partial derivatives are 0. So you set your partial derivatives to 0, and you get 2 equations and 2 unknowns. But when you're solving 2 equations, 2 unknowns, just remember you have a few basic strategies: substitution and factoring. So if you have to solve this, and I don't know if you have to or not, but if you do, then those are your go-to tools. Once you've found them, then you go into your classify, and basically you channel the second derivative test. We call this the second partials test because it uses second derivatives. And all right, there is no first partials test. So you have to use the second derivatives. And you look at this expression, fxx fyy minus fxy squared, and it comes down to saying what's going on. If it's negative, then you have a saddle. Okay, great. And a saddle, well, I just want to show off my drawing skills one last time. That's something that looks like that, right? Saddle shape. It's neither max nor min. In one direction it's a min, one direction it's a max. If it's 0, we don't know. Now, if it's positive, it's a max or a min, but it's not enough, right? So you got to go one level further, and you say, look in a slice. And that's when you channel your Calc 1 test, which says, oh, if your second derivative is positive in the slice, it looks like this. So that means your second derivative is positive, you're at a min. And if your second derivative is negative, then in the slice, you look like that, so you're at a max. All right. And then I think the only other thing that I saw, make sure to know how to do absolute max or min. And that's your making a list, checking it twice, going to find out which points are nice. So, make a list. What you're doing is, when you're finding absolute max or min, it says, I know somewhere there's a max and there's a min. So I just have to figure out where to look. So you look at where the gradient is 0, and that handles the whole interior. And then you get to the boundary. You say, okay, I have to handle each boundary curve separately, which makes this a kind of a longer problem. But the nice thing is, when you're on the curve, you can turn it from a problem of 2 variables to a problem of 1 variable using a parameterization. And so you say, okay, look for critical points on every boundary, and also always throw in the corners. That's your list. Somewhere on that list, the max and the min will occur. You don't have to do any of this. It's a waste of time. Once you've made your list, plug each one of these points into your function. Whichever one's the largest, that's your max. Whichever one's your smallest, that's your min. And there you go. All right, I think that's it for the second part of the course. Any questions on this segment of the course? All right, oh, good. You're confident about this one. Excellent. Excellent. All right. Well, that leaves just one last part to go. Now, this will look a little bit familiar. It's very similar to what we had before. Now, I'm calling this phase 3, but technically speaking, this part down here is not in it. Stokes' theorem and divergence theorem, those are separate. So, okay, so phase 3, if we're recalling where we're at. So first we started with geometry. That was the first phase. Second phase was differentiation. Third phase is integration. So, coordinate systems. The thing to remember about coordinate systems is the dAs and your dVs. So dA in Cartesian is dx dy, In polar, r dr d theta. dv, in Cartesian, dx dy dz. In cylindrical, r dz dr d theta. In spherical, rho sine of phi d rho d phi d theta. There you go. Now, you will probably see these show up. And the place where they tend to show up is in these types of problems, because they tend to use shapes that are easy to describe. They tend to like things like cylinders and circles and spheres. And so be prepared to work in a coordinate system to answer an integral. Here is my, I waved my hands before when I was talking about spherical and cylindrical coordinates, which say, and the reason I did it was to say, maybe you don't have to do the integral. Maybe you do, maybe you don't. But the nice thing is, if you're integrating 1 dA, you're finding area. If you're integrating 1 dV, you're finding volume. And really, if you're integrating a constant dV, what do you do?
Pull it out.
Yeah, you pull the constant out. So then it transforms. You don't have to work through the whole integration. You can say, do I recognize the area? Do I recognize the volume? Use geometry. Save yourself time. Know your applications. Most of them tend to be very physics-y at this point. So mass, integrate density. Moment, integrate distance and density. So distance has to be distance to something. So think about distance to what? Inertia, distance squared density. Again, distance to something. It'll specify. Your center of mass, you take your moments, divide by your mass, and look for symmetry. Know how to find arc length type integrals. That is your ds. So that's x prime squared plus y prime squared plus z prime squared dt. If this looks familiar, it might say, hey, isn't that like the magnitude of r prime? It is like the magnitude of r prime, because it is the magnitude of r prime. So no big surprise. Surface area, dsa, square root of fx squared plus fy squared plus 1 dA. Now, these show up in line integrals and surface integrals, but you can also see them directly. You might have a problem that says, find the surface area. Well, that's really just doing a surface integral of 1. In which case you say, oh, I have to integrate this kind of expression. So be prepared. So you say, hey, I can handle surface area, no worries. Div and curl, you know they're coming because you know they're coming. I mean, Stokes' theorem is a curl. Divergence theorem is divergence. It's in the name. So you know how to take those two expressions. Know how you have conservative functions and potential functions. So if f is a gradient of a function, well, little f is your potential, big F is your conservative. And these are useful for line integrals in the case that you have a conservative function. How do you find your potential? Well, one thing that might happen is they might give it to you if they were feeling very generous. But if they weren't, you say, that's no problem. I can find it for myself. What I can do is I can look at my pieces of f. The pieces of f are partial derivatives. And I start integrating. And I integrate my partial derivatives together. And when I sew them all up, and I integrate each one, check for consistency, and put them all together. That's not too bad. Know how to set up bounds or change bounds for integration. And again, I think we'll probably lean to, if you need to set up bounds, I think for most of those problems, if I recall, we added a picture. So know how to read pictures. But even if you didn't have a picture, if there's no picture, it's going to be because it should be a very simple description. Your description of your region might come from just say, what are the curves or the surfaces involved? Draw a picture if one's not provided. label the curves as needed, and find new descriptions. And remember, you can get old descriptions from bounds. So when we have like a triple integral, each layer is telling us something. So the outer layer is going between two numbers. The middle layer goes between two curves. The inner layer goes between two surfaces. All right. How are we doing? Any questions so far? As we round our corner, the end is near to me rambling. Line integrals. All right, so know how to work with line integrals. Now they come in a few flavors. You might have a very, I don't want to call it tedious, but it's what it is. The integral along a curve f x y ds. Well, in this case, you're going to convert everything to t. So x becomes whatever your parameterization is of t, y becomes whatever your parameterization is of t, and the ds, that's your various arc length pieces. And then you have to work with it. Why I call it tedious is you have a square root here, and that tends to not be nice. What is nice is when you start throwing in curves which have some sort of orientation involved in the line integral. So something like an fxy dot t ds. And I should have called this a capital F. There we go. Fix it there. So the integral along the curve of m dx plus n dy. Now, how do you integrate such a function here? It's the same idea. In the first case, we put everything in terms of t. In the second case, you put everything in terms of t. So it's like, cool. So what is your m? Well, m is a function of x and y. So everywhere you see an x, you put in what your x of t is. Everywhere you see a y, you put what your y of t is. dx becomes x prime. Same thing happens with n. It's a function of x and y. Everywhere you see x, put your x of t. Everywhere you see y, put your y of t. dy becomes y prime. So if you're doing a line integral, the idea is use your parameterization and put everything in terms of t in both cases. Now, pro tip. If you have to do this, and you may have a line integral that you have to actually do the long way. In other words, you may have a line integral where this does not work. You have to have a parameterization. Use nice parameterizations. Don't be like, I want to be exotic. And I'll start pulling out cosh and singe and like, no. Be nice to yourself. Be nice to your grader. Choose simple parameterizations. Well, whatever we do with lines, we can do similar things with surfaces. So we can integrate a surface integral. We have some function dsa. Again, we're rewriting everything in terms of x and y. We're thinking of this surface as being over a region in the xy plane. So it's essentially, the spirit of it is we're parameterizing the surface using x and y, where the parameterization is where we lie over in the plane. Well, just like we had a nice case when we did dot t, we have a nice case when we do dot n. In this case, the complicated thing up here went away, and now the complicated thing here goes away. So it becomes minus mfx minus nfy plus p. That, of course, assumes you have upward pointing normals. And remember, orientation matters. If you change orientation, then you change the sign. So if they give you a weird orientation, you say, okay, I'm just flipping my orientation, toss in a minus sign. So we're in our last stretch here. Variations of our fundamental theorem of calculus. Well, we have the fundamental theorem of line integrals. If we integrate along the curve, some function which is conservative, right, because it's the gradient, dot t ds, then that's f of b minus f of a. We just plug in. And b and a here are your endpoints. They're the boundary of your curve. And it's possible to bring your own curve. But we tend to save that for the third exam, not the final. I like to think we make the finals a little bit more straightforward. So the ones that are more involved tend to show up less often. We have Green's theorem, and that's for the plane. which says, suppose you have a region in the plane, then the integral around the boundary of the region of m dx plus n dy is the integral in the region of n sub x minus m sub y. Just check orientation. Do you remember the song? To the left, to the left. When you walk the curve, keep the region to your left. Right? Good. Good. This is a very musical class. Not like Calc 2. That's why Calc 2 is so hard. Not enough songs. We have to work on that. All right. Now, Green's theorem works for the plane. Stokes' theorem works for space. And it's essentially Green's theorem in exciting 3D. So you say, okay, what's going on? You have a surface, so you have the boundary of the surface. And you can do a line integral on the boundary of the surface. That's what this looks like. But then there's an extra m dx, n dy, p dz. You can say, hey, instead of doing that, I can do the curl dot n. Now you might say, but you might have a terrible surface. So what do? Bring your own surface. So if you see a Stokes' theorem question, the first thing you do is, did they give you a surface? If they didn't, put one in and bring the nice one. If they gave you a surface, you say, I don't like that one. Let me replace it. And just keep track of orientation so that you're consistent with the boundary. And all right, then the last thing is divergence theorem. Now, divergence theorem, you can usually almost always tell. There's a few clues. One is you see solid. All right, that's a good clue. You see this integral on the boundary of the solid of f dot n. So that's the flux through the boundary of the solid.